Hello friends. Today we will study about the application of Huckel molecular orbital theory of conjugated system to 1,3-butadiene system. We have already learned about Huckel molecular orbital theory of conjugated systems. Now we are applying it to different systems like ethene, 1,3-butadiene, cyclopropenyl and cyclobutadiene system, etc. So today we will learn about the application of this theory to 1,3-butadiene system, and we will calculate the different wave functions, energy, bond order, free valence, charge density, etc. So 1,3-butadiene, as you know, it consists of 4 carbon 2p orbitals and 4 pi electrons in the molecule. As you can see the structure, the skeletal system may be represented as CH2 double bond CH single bond CH double bond CH2, and the skeletal system C1 double bond C2 single bond C3 double bond C4. So you can see here that 4 carbon atoms, these are sp2 hybridized, and they have 2p orbitals and they have 4 pi electrons. So if we just see the structure of this 1,3-butadiene system, so it is not the planar one, as we know. Now how it is being established, so we can learn it with the help of the quantum mechanics. Now the HMOs are of the form psi I is equal to AI1 P1 plus AI2 P2 plus so on AIN Pn, or we can write it in the form of summation of R is equal to 1 to n AIR and PR. Here PR is the 2pz atomic orbital of the Earth carbon atom, and AIR is the coefficient of this R atomic orbital in the ith HMO. So if we see that if we take this as I, so it would be I1. How many number of carbon atoms are there? So according to that, this n number it varies. Now here we see that there are 4 carbon atoms, 1, 2, 3 and 4. So we can write the HMO in the form psi is equal to A1P1 plus A2P2 plus A3P3 plus A4P4. So n total number of carbon atoms is here 4. So we may write it till 4. So equation number 1 may be represented in the form. Now how we can determine the secular determinants? So secular determinants may be determined as follows, as we have already seen that A1. Now A1, this is the first orbital, and this one this represents the first carbon atom. So H11 minus ES11 plus A2. So first orbital and second carbon atom, so 1 2, again S12, so first orbital and second carbon atom. Likewise, first orbital and third carbon atom, first orbital and third carbon atom, and similarly first orbital and fourth carbon atom, and first orbital and fourth carbon atom. So first equation number 2 may be given in this form. Now equation number 2 for the second orbital, H21, means 2 is representing the orbital and 1 is representing the carbon atom. So 2 1, again second orbital and second carbon atom, likewise second orbital and third carbon atom, and similarly second orbital and fourth carbon atom. Now next is the third orbital and first carbon atom. Now third orbital and the second carbon atom, third orbital and the third carbon atom, and similarly third carbon atom and the fourth carbon atom. Now fourth orbital and first carbon atom, and likewise we may write the equation second, third, fourth and fifth, and about it we have already studied how the secular determinants are formed. Now if we want to write the corresponding secular determinants, means we will remove this A1, A2, A3 and A4. So we can write it now H11 minus ES11. From here H12 ES12. Similarly from here H13 ES13, and here H14 and ES14. Similarly from the second equation, third number equation, so H21 minus ES21, H22 minus ES22, H23 minus ES23, and H24 ES24. Now from fourth equation number, again we may take the H31 minus E as 31, H32 minus E as 32, S33 minus E as 33, S34 minus E as 34. And similarly from equation number 5 here, so H41 minus E as 41, H42 minus E as 42, H43 minus ES43, H44 minus ES44. So thus the corresponding secular determinants may be written like in this way, and that is equated to 0. So equation number 6. Now following approximations were made by Huckel, as we have already learned about it. Several integrals were given. Here atoms R and S are just neighbors. So neighbors means they are directly bonded. So here we can see if they are, it is the same number of carbon atom, then we represent this integral as alpha. Then second one is RS, means they are directly bonded, they are just neighbors, 1 2 2 1, 3 4 2 3 likewise. Then it will be represented as beta. Then SRR means R is the means S11 or S22 or S33 likewise. So we may represent this integral as 1. And then RS means if it is 1 2 or 2 3 or 1 4, whatever it is, if they are different, they are directly bonded or not directly bonded, then that would be equal to 0. So from this equation number 6 we may write down now as you can see here H11. If it is the same, then we have written it as alpha. If it is similar, then we have written as 1. So alpha minus E. So you can see here that we have written instead of it alpha minus E. Then the second term H12. H12 again directly bonded it is, so it would be represented as beta. Beta minus E, S12, SRS was 0, so multiply by 0. So beta minus E into 0, that would be equal to beta. Then H13, now not directly bonded, H13 is not directly bonded, so not directly bonded, or S13 it is also not directly bonded, so that would be equated to 0. So you can see here that alpha minus E, beta minus E into 0, then because it was H13, so it is 0. E into S13 is also again 0. Now this one was H14, so it is 0 minus E into 0. Now similarly you can see from equation number 6 that H21, again it is directly bonded, so it would be written as beta. Now H21, S21 it is 0, so beta minus E into 0. Now H22, they are the same one HRR, so it will be written as alpha minus E S22. Again they are the same, so it would be 1. So E into 1, so alpha minus E. Now H23, it is directly bonded, so it would be written as beta minus E into 0. H24, it is not directly bonded to 4, so it would be equal to 0 minus E as to 4, not directly bonded, so it would be equal to 0. So H31 again not directly bonded, 32 it is directly bonded, so it would be equal to beta. Similarly 33 it is for the same number of for the same number, so it would be represented as alpha, and 34 it is directly bonded, so it would be represented as beta. Now 41 it is not directly bonded, 42 it is not directly bonded, 43 it is directly bonded, so it would be written as beta, and H44 again for the same number, so it would be written as alpha. Now you can see from here, so alpha minus E, beta, and 0 0, beta minus E into 0, that would be equal to 0, alpha minus E, beta. Similarly we have seen that H, it was 3 1, it was 3 2, so directly bonded, so we have written here beta. And then H33 was, so it will be written as alpha, and S33 will be as treated as 1, so beta minus again E into 0. Similarly, first one was H41, so it would be 0, 42 it would be 0, 43 it is directly bonded, so it would be written as beta, and alpha minus E, so 444 H44 and S44, so it would be written as 1. If we made an assumption that alpha minus E by beta is equal to X, so we can write the value of the E from here. So previously, as we have seen these determinants from equation number 7, so if we divide it by beta, then what would happen? Alpha minus E by beta, so that would be represented as X, so we have written here as X. Then beta by beta, so beta by beta it will be equal to 1, 0 by beta it would be equal to 0, 0 by beta it would be equal to 0. Similarly, beta by beta, again 1, alpha minus E by beta, that would be equal to X. Beta by beta it would be equal to 1, and 0 by beta it would be equal to 0. So 0 for 0, beta by beta is equal to 1, alpha minus E by beta is equal to X, beta by beta is equal to X, and similarly 0, 0, 1 and X. So we can write in the form of the X this determinant. Now on expansion of this, we get the fourth degree polynomial, which may be represented as x4 minus 3x square plus 1. So you can see here, if we want to solve it, then how we can solve, and it clearly represents that there will be four roots, and hence it will have four energy levels, because it is fourth degree polynomial. So there will be four roots, and hence it will have four energy levels. So this equation can be solved easily by putting as y is equal to x square. Now y is equal to x square, then above equation it may be written as y square minus 3y plus 1. Here we can write y square, instead of x square we can write y, and plus 1 is equal to 0. Now this equation will have the following roots, two roots, that is x is equal to, we know the formula for it, so x is equal to minus b plus minus b square minus 4ac by 2a. So y1 is equal to, now we put the value of b here as 3 plus, because it is plus minus, so first we will write down for the plus value, then we will write down it for the minus value. So b square is equal to minus 3 whole square, so that would be equal to 9. Then minus 4ac, so 4 into 1 into 1, so that would be equal to 4, so it would be equal to 3 plus root 5 by 2, or we can write it 1 plus root 5 by 2 whole square. So we can solve it in this way. And similarly y2, here we will put the negative sign, same equation, so 1 minus root 5 by 2 whole square. Now we know that x is equal to plus minus root y, from y is equal to x square, so we may write it in the form that x is equal to plus minus root y. So we will have two values for this. So four roots, how we can get, so x1 x2 is equal to plus minus y1, and similarly x3 x4 is equal to plus minus y2. So here we will put the value of y1, so y1 is equal to um, y1 is equal to, so 1 plus root 5 by 2, or because it has two values plus minus, so we will get, when we will solve it, then we will get plus minus 1.618. And similarly for x3 and x4 values, when we solve it, then we get it plus minus 0.618. So in this way four roots can be obtained. Now we know that the alpha minus, the formula which we have already given about it, that is alpha minus E by beta is equal to x, so we can determine the value of E from here. So here we get the value E minus alpha minus x into beta. So we will put the value of x one by one. So as you have seen that we have already obtained the value of x as minus 1.618, then plus 1.618, minus 0.618, and plus 0.618. So we will uh, arrange it in the increasing order. So first we will put the value minus 1.618. So alpha minus 1.618 multiplied by beta. Then the second value which will come next to it will be equal to alpha minus, if we will put minus 0.618, then it would be equal to alpha minus 0.618 beta. And similarly next, if we will see, then the third value will be obtained by putting the value of x plus 0.618, and E4 is equal to fourth value, that is equal to 1 plus 1.618. So alpha minus plus 1.618 beta. If we solve it, we see the increasing order. E1 alpha plus 1.618, that is the most stable one. So first energy level, then second energy level, alpha plus, if we will solve it here, the alpha plus 0.618 beta, this one is alpha, and E3 is equal to alpha minus 0.618, and E4 is equal to alpha minus 1.618. So we can get the value for the energies for different levels, that is psi 1, psi 2, psi 3, and psi 4. So these are the HMOs level of 1,3-butadiene. From in this we have shown the energies of different levels, different 4 levels likewise. Now, how we can calculate the total energy? So if you see that we have already seen that there are 4 pi electrons. So 2 electrons will occupy in psi 1 level and 2 electrons will occupy in psi 2 level. So here you can see that if we want to calculate the total energy, then E pi, as 2 electrons have occupied the E1 level, that is energy is equal to alpha plus 1.618. So 2 into alpha plus 1.61, and 2 have occupied the second level. So the energy is there, alpha plus 0.618 beta. So we will multiply by it too. So total, if we will calculate it, then it will come out to be 4 alpha plus 4.48 beta. If we will calculate it, then it will come out to be 4 alpha plus 4.48 beta. Now if we want to calculate the pi bond energy, then for E pi is equal to 4 alpha plus 4.48 beta minus 4 alpha. If there would not be double bond, they all will be single, then the energy would be equal to 4 alpha. So if we deduct this value, then pi bond energy we can calculate, that is equal to 4.48 beta. Now how we can calculate the delocalization energy? So the total energy is 4 alpha plus 4.48 beta, and minus, supposingly if the 2 electrons were free, then 2 into 2 into alpha plus beta energy would be there. So if we deduct the this energy from the total energy, we get 0.48 beta. So this 0.48 beta, which clearly indicates that it is the delocalization energy. So what we were assuming as the localized structure means the double bond is in between the C1 and C2 and C3 and C4, and C2 and C3, between C2 and C3 there is a single bond. So it was the localized structure where we can see the energy as 2 alpha plus beta, which we have written here, plus 2 alpha plus beta. So 2 into 2 alpha plus beta. But this shows the means the energy, delocalization energy, when we calculate, it comes out to be 0.48 beta, which means it is not the localized structure, it is the delocalized structure. Delocalized means there is a double bond uh, that is being distributed among all these characteristics. So C1, C2, C3, C4. So we cannot localize the double bond between C1 and C2 and C3 and C4. So it is the delocalized one, and here the energy may be given as, so 2 alpha plus 0.48 beta.